A star can take 1,000,000 years to die and only 1 second to explode. That sentence sounds like a contradiction, but it's exactly what makes stellar death one of the strangest processes in the universe. We tend to picture a star's ending as a single dramatic moment, a flash of light, a boom, gone. That's not how it works. Death for a star is a slow unraveling that stretches across unimaginable spans of time, followed by a final act so fast your mind can barely process it. Today, we're going to slow that process down, frame by frame, phase by phase. We're going to watch a star die, not as an event, but as a story. And by the end, you'll understand why the corpse a star leaves behind can be even stranger and even more important than the star ever was while it was alive. To understand how a star dies, you first have to understand what keeps it alive in the first place. Every star is really a battle. Gravity is constantly trying to crush it inward, and nuclear fusion, happening in the core, is constantly pushing back outward, converting hydrogen into helium and releasing enormous energy in the process. As long as fusion keeps producing outward pressure, the star stays stable. It's a balance, a standoff that can last billions of years. But that balance is temporary. Fuel runs out, and when it does, everything changes. For a star like our Sun, the ending begins quietly. Once the hydrogen in the core is exhausted, the core contracts and heats up, while the outer layers expand outward. The star swells into what astronomers call a red giant, sometimes growing large enough to engulf its own nearby planets. This isn't science fiction. It's the expected fate of our own solar system, billions of years from now. Here's where the first twist comes in. You'd expect a dying star to get dimmer, weaker, fainter. Instead, in this phase, it gets bigger and brighter. A red giant can be hundreds of times larger than the star it once was. Death, for a star like the Sun, doesn't start with fading away. It starts with expansion. Eventually, the outer layers drift off into space entirely, forming a glowing shell of gas called a planetary nebula, a term that's actually misleading since it has nothing to do with planets. What's left behind is the exposed core, a white dwarf, an incredibly dense, slowly cooling ember about the size of Earth, but containing roughly the mass of the Sun. From there, a white dwarf doesn't explode, it just fades, quietly, over trillions of years, longer than the current age of the universe itself. That's the fate of an average star, but not every star gets to die peacefully. Massive stars, ones far larger than our Sun, follow a completely different, far more violent path. And this is where the story gets intense. A massive star also fuses hydrogen into helium, but it doesn't stop there. Once helium runs low, gravity compresses the core further, and the star starts fusing helium into carbon into neon, then oxygen, then silicon. Each stage happens faster than the last, and each element produces less energy than the one before it. It's like a fire running out of good fuel and burning through scraps just to survive. By the time the core starts fusing silicon into iron, the star is in serious trouble, and most people don't realize why. Iron is the point of no return. Fusing iron doesn't release energy, it absorbs it. The moment a massive star's core turns to iron, the outward pressure that had held the star together for millions of years simply stops. And that's when everything happens at once. The core collapses in less than a second, an actual, literal second, falling in on itself so fast that outer layers of the star are still unaware anything has changed. Then the collapse reaches its limit, rebounds violently, and triggers one of the most powerful explosions in the known universe, a supernova. For a brief window, that single exploding star can outshine an entire galaxy of billions of stars combined. It's not an exaggeration, it's physics. And the debris from that explosion doesn't just disappear. It gets hurled outward at incredible speeds, seeding surrounding space with heavy elements, carbon, oxygen, iron, gold, elements that didn't exist before that star forged them. Here's the part that tends to stop people in their tracks. Much of the calcium in your bones and the iron in your blood was created inside a star that died exactly in this way, long before our solar system even existed. You are quite literally built from the wreckage of a stellar death. So the star explodes. Story over? Not even close. What happens next depends entirely on how massive the original star was, and this is where the science gets genuinely strange. If the leftover core after the explosion is roughly 1.5 to 3 times the mass of the Sun, it doesn't just sit there. It collapses into something almost impossible to picture, a neutron star. Imagine squeezing the mass of the Sun into a sphere only about 12 miles across, roughly the size of a city. A single teaspoon of neutron star material would weigh about as much as a mountain here on Earth. These objects spin incredibly fast, some rotating hundreds of times per second, blasting out beams of radiation like a cosmic lighthouse. We call the ones we can detect from Earth pulsars. But if the leftover core is even more massive, more than around 3 solar masses, gravity wins completely. Nothing known in physics can stop the collapse. The core doesn't just shrink, it keeps shrinking forever, compressing into a point of infinite density that warps space and time around it so severely that not even light can escape. That's a black hole. And it's not some separate cosmic phenomenon unrelated to stars. It's simply what happens when a massive enough star finishes dying. This is where a common misconception needs correcting. Black holes are often imagined as cosmic vacuums sucking in everything nearby. That's not accurate. A black hole only has as much gravitational pull as the mass it contains. If our Sun were somehow replaced with a black hole of equal mass, Earth would keep orbiting exactly as it does now. The danger isn't distance-based hunger, it's what happens if you get too close to something that dense. So depending on how a star lived, it can end up as one of 3 profoundly different objects: a slowly cooling white dwarf, an ultra-dense spinning neutron star, or a black hole that bends the fabric of space itself. Same fundamental process: nuclear fusion, gravity, collapse, but wildly different endings, all determined by one variable: mass. And here's the final twist, the one that reframes everything we've just covered. We've been calling this a death, but almost nothing about it is truly an ending. The gas and heavy elements blasted into space during a supernova eventually cool, drift, and collapse under gravity to form new stars, new planets, sometimes even new solar systems. The raw material of our Sun, our Earth, and every living thing on it was recycled from stars that died in explosions like this over 4.5 billion years ago. So when a star dies, it isn't erased from the universe, it's transformed. Its final explosive moment becomes the starting material for the next generation of stars and planets, quite possibly planets with their own oceans, their own atmospheres, their own forms of life, built from the same forged elements you're made of right now. A star's death takes millions of years to arrive, less than a second to happen, and then echoes across billions of years afterward, scattered through every future star, every future planet, and possibly every future person who ever looks up and wonders where it all came from. The next time you look up at the night sky, remember this: some of that starlight is coming from suns that are already dead, and some of what makes up your own body once belonged to one of them too.